So the first results we are going to see today are results about roots of unity, which will be useful later. In particular, there will be an immediate application, but then they will be useful later. The reason why we are interested in roots of unity is because we have seen early on in the course that if you take the image of an element of a finite group of order n, say, under any representation, so rho of G, then this matrix, say, can be put in diagonal form with nth roots of unity on the diagonal. So the first lemma, whoops, why red? The first lemma we are going to see today says the following. Consider complex numbers z1, zn, okay, all of absolute value 1. So this is slightly, this is actually weaker than saying that the Zi are roots of unity. Of course, if the Zi are roots of unity, then they will have absolute value 1. And then the theorem tells you that if the absolute value of the sum is n, then the Zi are all equal. Perhaps I should make a comment which will then be useful in the proof. By the triangle inequality, the sum of this, the absolute value of the sum will be less than or equal to the sum of the absolute values. Since each have absolute value 1, this will be, in any case, less than or equal n. So under the assumption that if the Zi, under the first line of the assumption, if the Zi have absolute value 1. So this claim here is saying that, well, no, red, I want it in red. It's saying that the maximum is of the absolute value is reached here. That is, we have all these objects, all these Zi, okay, of absolute value 1. So, well, this is supposed to be a circle. I think I can do slightly better than this. Okay, so they all lie on the circle of radius 1, center in 0. And the point is that the only way for their sum to have absolute value n is when they are aligned, okay, when they are pointing the same direction, something like that. Otherwise, you lose something. Let's see the proof. So the proof goes like this. Let's take two indices. Two different indices among these indices we range from 1 to n, okay? And then you consider this sum and you rearrange it, okay, as Zi plus J plus the others. Of course, these are n minus 2 elements, okay? So the triangle inequality tells you that this is less than Zi plus J, plus the sum of the others, okay, and so you see, if you know that this is n, okay, the point is this will be less than 2 by this line that we saw here, okay. If you have say any number of elements of absolute value 1, the absolute value of the sum is at least the number of items you have. So it will be 2 plus n minus 2, okay? So if it is exactly n, this means that this sum is also 2, because if it's less than 2, this will be less than n, okay? So for this sum to have absolute value n, you need that for each I and j distinct indices, each sum has absolute value exactly 2, okay? I think it's clear. If in this inequality you have a stricter less than, then this won't reach n, okay? So for each I different from j, we have zi plus zj equal to. Okay, good. So what does this mean? Well, they have absolute value 1. So we know that we can write the zi as a complex exponential in e phi I and zj equal e I phi j, where this phi I and phi j are angles, okay? So you can take this from 0 to 2 pi, okay? It's the usual formula for, I mean, e to the ix, where x is, so these are real numbers, to the ix, for x real, runs around the circle of radius 1 in the complex plane. And since clearly the sum of complex numbers is commutative, we can assume that phi I is greater than phi j, okay? One of them will be greater than or equal to. In the end, they will have to be equal, okay? So we simply call zi the one with the largest angle in this range. Good. So let's consider okay, so we have zi and zj. Well, I and j. Okay, sorry, I knew I was having the indices wrong. So let me correct the index. This I becomes a k. The reason being, of course, that the I is taken by the complex, by the imaginary unit, and otherwise it's confusing. Okay. And let's say that, okay, okay, fine. Let's say that phi j is greater than or equal to phi k, okay? So, well, sorry, I left this page too quickly. So we have these two elements of absolute value 1, and I assume that the value of the angle for this is greater than or equal to the other. I mean, it's just a matter of convention. And so let's see what zj, plus zk looks like. So remember, I remind you in a second, this must have absolute value 2, okay? So this is e to I phi j plus e I phi k, okay? So I collect, I collect e I phi k, and what I get is 1 plus, actually the other way around, e I phi j minus phi k plus 1, okay? And of course, we have the Euler's formula. So this, let's use a shortcut. No, not a shortcut, I mean a shorthand. So let's call phi this different of the angles. Okay, so this is the angle between zj and zk, this phi. So what we get is, well, in front we have this, okay? And then Euler's formula tells you that this will be equal to the cosine of phi plus 1. Okay, so the cosine comes from here, the 1 comes from here, plus I sine of phi. Okay, we have used the Euler's formula. Okay, Now, this element has absolute value 2. Okay, the triangular inequality, we prove this. Oh, this has now this has absolute value 1. Well, okay, let's write it like this. This is 1, and then this means that this has absolute value is absolute value 2. Okay. And so this is absolute value 2. For simplicity, we take squares. Okay, so we take the square of the absolute value. So taking squares, you have that 4, the square of this, equal cos phi plus 1 squared plus sin phi squared, because otherwise I would have to take a square root. So let's square, so we have an identity in real numbers. Yeah, okay, whatever. And cos phi squared plus sin phi squared, and then there's plus 2 cos phi plus 1. Okay. And what we get, of course, there's no need to say that this is 1. And so there's 1 here. So 2 cos phi plus 1. Okay, let's finish on this page because it's clear. So we obtain that this is this is 2. Okay, and this means that am I right? Just a second. Oh no, sorry. This is 2, yes. And so cos phi has to be 1, okay? Because if this 2 clearly, and cos phi equals 1 means, okay, note that this is greater than or equal 0 because I had chosen phi j to be the greatest of the 2, okay? So phi j is greater than or equal than phi k, and so this means that the angle phi is 0. And of course, the angle phi being 0 means that phi j equal phi k. And so this means that that zj equals zk, okay? Because this is zj and this is zk. Okay, I mean, they differ only, say, by the angle, and we prove that the angle has to be the same with this trigonometric equality. And j and k were simply two arbitrary indices here, okay? And so we have seen that any two of them are the same. So all the z are the same, okay? So if the sum of elements of absolute value 1 as absolute value n, which is the maximum that you can have, the only way to get this if they are aligned, okay? If they go in the same direction. If you have two elements going in two different directions, then their absolute value will be less, okay? It's something really about vectors, okay. Right, the other lemma we have is says the following. This will be useful in several situations. This time we take omega 1, omega n to be roots of unity. So it's complex numbers which are roots of unity. It doesn't matter which roots of unity. Of course they have absolute value 1 since they are roots of unity, but of course this is more restrictive hypothesis than the previous one. And since they are roots of unity, they are roots of say, I mean, in the end, in the course of the proof, I'll say that they are kth roots of unity. And so they are roots of xk plus minus 1, so they are algebraic integers. But the lemma says something. Consider this elements, you sum this omega 1, omega n. So far you have an algebraic integers, but then you divide by n, okay? And of course, you cannot be sure that this is an algebraic integer. I mean, for instance, take 1, okay, the integer 1. If you divide this by, this is of course an algebraic integer because it's the root of x minus 1. But if you divide by n, well, okay, by n greater than 1, then you don't get an algebraic integer. You get a rational number. Okay, so if this is an algebraic integer, it's actually an if and only if, then there are two possibilities, okay? Possibilities. One is that this is 0. Of course, this can happen. For instance, if, example, it's very trivial. If the omega I are just 1 and minus 1, then you may have 0, okay? So these are second roots of unity, their sum is 0, and this is okay. Or they are all equal. Sorry, let me write it correctly. Okay, and then you have the sum of equal objects divided by their number, so the average is just alpha. And then you get that the equal alpha. And then clearly, if they are all equal, then alpha is an nth root of a root of unity, okay? Because it equals any of them, okay? So let's say if they are equal, then this holds, and so it's an if and only if, of course, because if they're all equal, then alpha is one of them. I mean, they're all equal, and then it's an algebraic integer. Let's see the proof. So, okay, so the omega I will be roots of unity, say, k's root of unity for different k's. But of course, if you take the least common multiple of all these k's, you'll get they are all roots of unity with respect to that number. Okay, so for instance, if one is the second root of unity and another one is the third root of unity, then they are both sixth roots of unity. Okay, because if something squared is 1, then something to the sixth is 1, and similarly, if something to the cube is 1. So assume that the omega I are kth roots of unity for some k. And what we do, we consider the splitting field. Of the polynomial sk minus 1 over q inside the complex numbers. So we take the kth root. This is something we have already done yesterday. We take the kth roots of unity in C and take the field generated by them. Okay. So by reasons that we have already recalled yesterday, E over Q is a Galois extension because it's the splitting field of a separable polynomial, of a polynomial in characteristic 0, which is automatically separable, and the Galois group we saw yesterday, abelian. I cannot remember whether this is useful. Well, abelian. With abelian, I mean, it's abelian, but I don't think we're going to use it. Okay. And of course, and clearly, alpha is in E. Let me get back once you had a chance to write this down, because of course the omega I are in E, and then it's an extension over Q, so you can divide by N, and you're still within E. Okay. Now, an element of the Galois group, which I will call G, I think an element G of G, maps roots of unity, kth roots of unity, to kth roots of unity. Well, that's clear because it fixes the elements of Q. So if you have omega k minus 1 equals 0, you apply G, and G is a homomorphism. Okay, this should be trivial, and so respect all the operations, so you get this. Okay, so omega to the G will be again a kth roots of unity, and so this means that alpha to the G will thus have a form similar to that of alpha. Recall that alpha is omega 1 plus omega n divided by n, so when you apply G, well, the omega I will go to other kth roots of unity, but it will be the sum of of n kth roots of unity divided by n, except that the particular roots of unity will have changed in alpha G. Okay, and note that this is the same inequality we have just seen. If you consider the absolute value of this, this will be the absolute value of the sum over here, and divided by n. Of course, this is an integer, so its absolute value is itself. And note that, I mean, as usual, the triangle inequality is the same inequality we used in the previous lemma. All of these are roots of unity, so absolute value 1. So, okay, so let's do the step. Intermediate step, trivial as it is. So on top you have n, on the bottom you have n, and so in the end this is 1. So alpha has absolute value at most 1, okay? And since the alpha to the G have the same form and the same, okay? So if you put the two together, you obtain that alpha to the G equals 1 for all G in G. And remember that G is my shorthand for the Galois group of the extension which you're working, okay? And now let's consider the following. I changed the notes in this part because I had written the notes 2 years ago, and in rereading them, I found several errors, I mean, things not quite correct. This is one of them. It is on page 22. This Formula 1.11.2, which I have changed. Okay, and so the correct version, which is incorrect in the notes was incorrect until a couple of days ago, is that now you consider the norm of alpha in E over Q. Okay, the norm in the extension. What's the norm? The norm is the product as G ranges. Recall this is the Galois group, which, as I said, is abelian, but I don't think it plays any role, is the product of all the conjugates. Conjugate meaning what you obtain from alpha when you apply the Galois group, okay? And why is the norm important? Well, there are some results that you have learned in Galois theory and in other courses about the norm, but the important thing is that this is a general fact. This is fixed by G. Well, clearly, because when you apply an element, well, okay, let's just recall why it's fixed, because if you apply H, okay, then the product becomes this. I mean, H is an isomorphism of E over Q, and of course, this is the same, okay? This is the same product, because by multiplying G by H, you're just permuting the elements, but you still have the same. So this is fixed by the Galois group. And so by Galois theory, an element, since this is a Galois extension, actually this is one of the definitions of Galois extensions, this means that the elements of the extension fixed by the Galois group are exactly the element of Q. So okay, and by hypothesis, recall that by hypothesis, alpha is an algebraic integer, and then so are the alpha G. This is an argument we have already seen. I mean, it's more or less the same argument we had to say that a root of unity is also sent to a root of unity by an element of the group, because saying that alpha is an algebraic integer means that alpha is a root of a monic polynomial with integer coefficients when you apply an element of the Galois group. Okay, you obtain that alpha to the G is a root of exactly the same polynomial, because the coefficients are integers, hence rational, and so they stay fixed, okay? So these are all algebraic integers, so this product is an algebraic integer. And you see how important is the very simple result we had recalled a couple of lectures ago. This is an algebraic integer, and it's rational, and then this means that it's an integer. Okay, algebraic integer plus rational means integer. Okay, it's a simple matter of polynomials. Okay, now the point is that as we saw in the previous slide, the absolute value of alpha is at most 1. And the alpha to the G have exactly the same form, so the same holds for the alpha G, okay? So, next page. So we have proved, we have shown so far that this is an integer, but all alpha G's have absolute value at most 1, okay? For all G, which recall this is the Galois group. And then this means that this object has absolute value at most 1, simply because the absolute value of a product. But there aren't many possibilities here, because it's an integer and the absolute value is just the absolute value. I mean, either it's the same as the original integer if the integer is negative, otherwise it's minus it. So there are two possibilities. So this is an integer of absolute value at most 1. The first possibility is that this product is 0. Of course, the product can only be, we are in the complex number, so a product can be 0 only if one of the factors is 0. And then, of course, you apply G inverse and you obtain that alpha is 0. And this was one of the possibilities. Recall, is what happens, for instance, when the two roots are 1 and minus 1 and you divide by 2. Or for instance, if you have if you take 3, if you take the 3 third roots of unity, their sum is 0, okay? Okay, so this is a possibility. The second possibility is that that this has absolute value 1, okay? Which means that it's either plus or minus 1. But if you have things that are absolute value at most 1, and the product has absolute value 1, by something we already, but an argument we have already seen, this means that the absolute value of each just a second. Okay, of each of these has to be 1. Because if the absolute value of one of these is less than 1, then the product cannot have absolute value 1. And in particular, it means that the absolute value of yes, for all G in G in particular, the absolute value of alpha is 1. But what's alpha? Alpha is the sum of this stuff divided by n, okay? And so to say that alpha is absolute value 1, it means that if you take the absolute value of the top, has to be equal to the absolute value of the bottom, which is n, okay? And this is exactly the first lemma, okay? The first lemma tells you that if you have elements of absolute value 1 and the absolute value of the sum is n, by the previous lemma, all these have to be equal, okay? And so they have to equal alpha, okay? So these are two simple lemmas, but there is an immediate consequence of this lemma, which is useful, corollary. Well, okay, I'll first describe the corollary and then I write the term corollary. We have seen that a character completely determines a representation, okay? And in one of the seminars, one of you will explain how to construct explicitly a representation which affords a character, a certain character. So in principle, you can read all the properties of a representation from its character, because as I said, the character determines the representation, and thus all the properties of the representation have to be there. And in particular, you can consider the kernel of a representation, okay? So if rho is a representation, a linear representation, of our group G, usual conventions, G is a finite group and rho is a representation, blah, blah, blah. So this is the G in G such that rho G is the identity, okay? And then if G is in Ker rho, okay, this means that rho of G is the identity, so it's 1, 1, 1. And so if you take the trace, the character of G will be equal to what? Well, of course, it will be the character of 1, okay? And the corollary says that the curl of rho is exactly the G in G, such that the value of the character of G is the same as the degree, okay? So here we have seen one implication, that the kernel is contained here, okay? So these are the column. That if an element is in the kernel, then the value of the character is the same as the degree, because it's just the sum of the ones on the diagonal. But we have to see the converse. So if chi G equal chi 1, then recall that rho of G, this is something that I just recalled at the beginning of the lecture, will be omega 1 omega, let's say n, okay? For, I mean, there is a basis. I mean, rho G can be put in diagonal form. There are zeros here which I don't write, and with the roots of unity on the diagonal. And so this tells you that omega 1 plus omega n equals n, okay? Because, of course, chi of 1 is the sum of n ones. And so this is even that they are equal, okay? They are equal, but in particular, if they are equal, the absolute value is the same. Okay, and so this means that all the omegas are equal. Say omega, because of the first lemma, okay? Because if you have a sum of elements of absolute value 1 whose sum has absolute value n, they have to be equal. And so what we have here, we have n omega, and so omega, so it follows that omega is 1. Okay, so this is the identity. So rho G is the identity matrix. Okay, because we have the sum of these roots of unity that are n, so you use the result that if the absolute value, of course, if the sum is n, then the absolute value is still n, so they are all equal, so this is just the sum of, I mean, n times omega, so it's just n times omega, and so omega is 1, okay? But simplify n. And so you see, here we see that you can read the kernel of a representation, okay, from its character. As I said, in principle, you can read everything about the representation from the character. It might not be obvious how you do it, but in this case, this is the simple recipe, how to read the kernel. Good. Now we discuss a bit the character table of a group. And we first prove a result that I'm not sure whether it's particularly interesting, but it is a proposition. But I mean, a variation on it will be of interest. Proposition, the character table of a group. Is a non-singular matrix. This is not probably important in itself. I'm not sure whether there are any applications, but a variation on it will be important. So recall what's the character table. So the character table is a square table where the row index is given by the irreducible character of G, and the column index is G, where these G are representative. So this is okay, representatives of conjugacy classes. Okay, chi of G. And so at the intersection of the row labeled chi and the column labeled G, you have chi of G. And recall that this is a square matrix, okay, square matrix, because the number of irreducible characters equals the number of conjugacy classes. We recall where this comes from, because this is the application we have in mind. So I want to prove that this character table is non-singular. So it's rather tempting to apply to this formula, where, okay, this is the orthogonality relation. It's the orthogonality, I mean, a particular case of the orthogonality relations. Well, yeah, okay, fine. No, just a second. Let's write psi here. And so let's say, okay, this is 0 if chi is different from psi, and 1 if chi equals psi, where chi and psi are both irreducible characters, okay? These are the orthogonality relations, or first orthogonality relations, because we will have the second one. So the temptation is to consider a matrix here. This is suggestive of an inverse matrix. So the temptation will be to have a matrix here where you have chi here, G here, so you have exchanged the two, and here you have chi of G conjugate, okay? Because then when you do the product, you have something resembling this. But this is not quite correct, because here we are summing over all elements of G, okay? And whereas here, if you take a product of a line here by a column here, you will only be summing over a set of representatives of conjugacy classes, okay? So you're only counting one element per conjugacy class. And then the trick is quite simple. You consider the following matrix. So G, again, is the representative of the conjugacy classes. Chi, again, is irreducible characters of G. And here you put chi of G conjugate, okay? But you multiply by the size of the conjugacy class of G, okay? So let's see what we get. The idea is simply to rewrite this. I'll first say it in words. So here we are summing over all elements of G. But as we know very well, conjugacy classes, I mean, since, the conjugacy classes form a partition of G. So you can split this sum over the conjugacy classes, okay? So, okay, let's rewrite this. So let's put it like this. Just a second. Let's C1, Cn, well, and why not, be the conjugacy classes of G. So a partition of the distinct. And so, and let Ci be Gi to the G, okay? Be the Gi is an element of the conjugacy class. So the conjugacy class is Ci is the conjugate class of Gi. So when you consider, when you consider this sum, okay, there's no 1 over G in front for simplicity, but we'll remember that it has to be there. So you can split it like this, since they form a partition. You sum first over the terms of the partition, and then inside you sum for G in Ci, okay, chi G. Sorry, that's Psi. Okay, so we are summing over a particular conjugacy class, and then we are summing over all the conjugacy classes. But the point is that the characters are class functions, okay? So this means that, okay, let's put it here. So chi of G is constant on each Ci, and actually chi of G thus is equal to a particular element you may have there. So remember, characters are class functions. So this is follows from the trace factor, from the fact that they are tracing. So what we have here then is that you sum over the conjugacy classes, okay? These values are constant on the conjugacy class. So you get the value of chi Gi, psi of Gi. And then here you have the size of the conjugacy class. So let's say something like that, okay? Because it's the same term repeated by the size of Ci, okay? Okay, so the idea is the following then, okay, let's go. I think I'll copy this formula and go to the next page. It's a bit big, but okay, there are 2 ends missing, but okay, so let's move this up, and let's add the missing ends. Yes, okay, fine. So the point is, we have the character table here. So chi ranging in the reducible character, and here you may say Gi, okay? So the Gi are defined in the previous slide. So here you have just chi of Gi, and then here you consider the matrix which has which has, as I said, in the GI chi position, the size of the conjugacy class times the conjugate of the value chi gi, okay? So if we consider the product of these two matrices, okay, this is just an index, okay? These are just indices, they don't enter in the product. It's the product of this matrix, okay? So, sorry, this matrix by this matrix, okay? Disregard this GI and chi, these are just the indices, just for clarity. So what's the typical product? So a typical, well, okay, let's put it like this, just to be, sorry, I made a correction. Let's say psi, okay, psi. Okay, so it's generic. So if you do multiply the chi line by the psi lines, but by the chi line by the psi column, what you have here, okay, when you do line by time this line, so in this position, you will get what? You will get exactly this, because you get the sum, okay, over for I ranging from 1 to n, because that's the column index, okay, 1 to n, of this, and then this, okay? And this is exactly what we have here, and this equals this term, okay? Okay, so let's rewrite it. And so what's this? Recall, this is the order of G, in a second, if chi is equal to psi, or 0 otherwise. So why the order of G? I'll be back on to this slide in a second, because the fact was that this sum was either 0 or 1, okay, but there is a 1 over size of G in front, and I have omitted it. So essentially, I've taken this equality and multiplied by the order of G. So when it's 0, it's still 0. When it's 1, multiplying by the order of G is the order of G, okay? So this equals this. So this means that this matrix here is a matrix that has order of G on the diagonal, and here 0. And then you see that the inverse of the character table is this matrix here multiplied by 1 over G. Okay, let's write this on the next. So I think this is clear. This is just the term here at the intersection of, in the product, the intersection of the chi row and the, so yes, I saw line, but because it's, yeah, but it's row and column, okay, and psi column is this object. And so we obtain a scalar matrix. And so this means that the inverse of the character, so the inverse of the character table is what? Is 1 over G, okay? And then this object, so the indices are GI here and psi here. And as I said, in the intersection, we have size of the conjugacy class times psi of G conjugate, okay? So we have proved that if you multiply the character table by, so this is just the value, okay? I haven't written here, but I have written outside, I mean, not to clobber this matrix. So this is the inverse, okay? So the character table is a non-singular matrix, but something that will be useful is a trick, because I mean, we had seen that is not enough to find the inverse of the character table to just exchange rows and columns and put a conjugate, because you need to insert the side of the conjugacy class. But this is sort of asymmetric, because I mean, this is stayed as it is, and this instead as the size. There is a symmetric way of doing it. And the symmetric way of doing it is consider the extended character table. And what's the extended character table? Well, okay, we have already some notation, but so the columns are the GI, so recall the conjugacy classes are the, well, I don't think I will need the CI, so GI to, okay, like this. So this is the column in this conjugacy classes. Here, as usual, we have the irreducible characters. And what do I put here? Well, again, I'll write it outside because otherwise it's not clear that it's just an element, but it's the element in the kith row and in the ith column, say, okay? Let's say that one runs, that I runs from 1 to n. And what we put here, we put, yes, chi gi. And then what we put the order of the conjugacy class, but we take the square root. And yeah, okay, we write it the smart way with the exponent 1/2, but of course it's the square root. Why is this interesting, this form? Because now we can see that, let's call this matrix T, okay? Okay, that, so this is a matrix which looks like a character table, except that I have taken the chi I, say, entry, I have multiplied it by the square root of the side of the conjugacy class. Because then, if you consider T multiplied by the conjugate transpose, okay, what does it mean? So here we have chi, I could write I or GI, let's write GI, okay? So here, okay, I'll write the element here. In this position, we have 1/2 times chi of GI. And then if you consider a conjugate transpose, this will be, let's take this away. This will be, so we have exchanged the two things, okay? So I write GI here, not to, because otherwise it looks like an extra term in the product. And if I take psi here, so you transpose, you see I've exchanged the indices, and so let's say that this is GJ, just to be generic, and I have conjugated. Of course, the conjugate has no effect on this, which is an integer, but here we'll have GJ to the G 1/2 psi of GJ. And now you see that when you multiply the two, okay, what happens when you multiply the chi-th row by the psi column here? So in the position, in the chi psi position, dot minus, let's say, let's use a slash. And then let's use a pair. In the chi psi position, in the product, we will find what, well, so the sum goes over the GI, okay? So 1 to n. Okay, so it's GI 1/2, okay? Chi of GI. And then there's the similar thing on the other side. Okay? Of course, the index has to be the same. And then you see that these two halves, these two square roots come together. So you get the sum that we already had in the previous. This is now a full size of the conjugacy class. Well, by now we have seen this formula a number of times. And so this means that this is the order of G if chi equals psi, and is 0 if chi is different from psi. Okay? And note that this is just the orthogonality relations, okay? At a certain stage today, we have learned that the orthogonality relations can be rewritten in terms of this sum of the conjugacy classes. I mean, it's the standard orthogonality relations, except that I've taken the order of G to the other side, and they have grouped together the elements which are in the same conjugacy class, okay? But now we use elementary, absolutely elementary linear algebra. So we have that if you multiply this matrix by this matrix, you get this matrix. So essentially the product. So this means that, let's go to the next page. So we have proved that T times the conjugate transpose is this, scalar matrix. Let's put big zeros here, okay? But then this means that this is, well, apart for the factor 1 over G, this is the inverse of this. Or if you wish, these matrices are then invertible, okay, non-singular, because their product is an invertible matrix. And of course, if their product is this, then you can conjugate, and the product in the other order is the same, okay? Because this is a scalar matrix. So when you conjugate by T, say, you exchange the factors, but this stays the same. You could also do this in terms of inverses. I mean, you divide by 1 over G, no, of the order of G. But this equality will now spell out, these are the second orthogonality relations. So let's first write them down, and then we will write a result, a lemma. So okay, so let's take a look again. So we have our two matrices, and we know that the product also in this order. Okay, first the conjugate transpose, and then the other will give you a scalar matrix with G on the diagonal. And recall, so the index here is Gi, here psi, so the index here is chi, and the index here is again, well, okay, Gj here, Gi here. So what's this time you have elements, this time in the product, you consider, so let's recall what you have here. In this position here, you have the size of Gj times psi conjugate Gj, and in the position here, you have the size of Gi times the value of the character chi on Gi. So this time the Ji element of the product is, so this time we sum over the irreducible characters, okay? Because these are the column index of the first matrix. We have exchanged the two terms, and the column and the row index of the second matrix. So what do you have in this position? So in the Ji position of the product matrix, we find what? And we find the sum, which is the sum over the irreducible characters, okay? So here we have Gj G chi conjugate. Let's write a conjugate. No, yes, okay, chi conjugate of Gj, okay? And on the other side, you will have Gi of G, chi of Gi, okay? And we have already seen that this will be yeah, okay. So we know that this is a scalar matrix, okay? So we will have order of G on the diagonal and 0 outside. So this will be the order of G if I equal J. Okay, if the two indices are the same. Because remember, I'll be back in a second. Here, we are taking the row J here and row I here. Okay, and the 0 if I is different from J. And you can reformulate this in a different way, because what we are telling is, we are telling that if we are taking the same conjugacy class, okay, then you obtain the order of G. If you're taking two different conjugacy classes, which means two different rows and columns, you get 0. So another way of putting this is to say that the sum over the reducible character of what? Of Z to the G, chi G conjugate. We can, sorry, chi of Z. Okay, yeah, okay. So when I say chi of Z, the conjugate, I mean, this is the same value over a conjugacy class, okay? And here you have W, G, oh, there's a, sorry, there's a 1/2 here. Let me circle in red what I have added. I have forgotten these halves. Let's see whether the halves were there. Yes, okay, sorry. Here the 1/2 that I have forgotten, okay? Sorry. So the red ones are the square roots which were needed. Otherwise you get order of G square. No, well, otherwise I get a mess. So W and chi of W. Okay, and so order of G or 0 if Z and W are conjugate. Because I equals J means that Z and W are in the same conjugacy class, okay? Because here I take a representative, but the value of the size or of the character is the same over a conjugacy class. So this gives you the order of G if these two are conjugate, okay? Because to say that I equal J really means that the two are conjugate. Otherwise, if they are not. Okay, but note that when it's 0, we can safely multiply by these two, and which are constant, they depend on the sum, and get nothing, and it will still be 0. And whereas when Z and W are conjugate, okay, let me take a copy of this. Okay. Yeah, I've saved most of it. So if Z and W are conjugate, okay, then of course Z, this order equals this, okay, because they're conjugate, they have the same conjugacy class, and the same goes to the square, and also the value of the character is the same, okay? So what we obtain that, okay, so this means that we obtain here sum over characters. No, well, I'll write it somewhere else. So this will be, okay, so if Z and W are conjugate, this will be order of G, okay? Then this we can take outside. No, well, just a second. Oh, yes. Just a second. Oh, yes, yes, yes. Okay. So just a second. Okay. So this will equal what? We can take this outside. These are equal. So it will be, well, in color, in red. Black. Okay. So it will be the order of the class, because you have two square roots and they are equal. Okay. Sum chi rg chi z chi w, okay, because this is the same. This will be the order of G, okay? And so we have obtained the second orthogonality relations. What I mean, note, remember, orbit stabilizer, which tell you that the order of G equals the size of an orbit time the order of the stabilizer. What a stabilizer in the conjugacy action is the centralizer in Z. Okay, so recall, I'll write it here. Recall, no, well, no, this is not what I wanted to do. Recall that the centralizer in G of Z equals the elements of G which commute with Z, okay? And this is the stabilizer in the conjugacy action. So you have orbit stabilizer here, you simplify, okay? And you obtain the second or the other orthogonality relations. So the other orthogonality relation, the order of the second orthogonality relations tells you the following, tell you that if you take the sum over the reducible characters of chi of z conjugate chi w, this will get the size of the centralizer if z and w are conjugate, or zero otherwise. Okay, and the reason is because here you divide by the side of the class, you obtain exactly this. And when this is zero, of course you multiply by whatever and you still get zero. Okay, remember, I'll put it in a corner, that this can also be written like this. Okay, because I mean we are talking. We have just discussed this has to do with the fact that if you take a root of unity, then its inverse and conjugate are the same, and this character is the sum of roots of unity. Okay, so we have found this result. But remember, these are just the orthogonality relations. It's just that we've used the linear algebra. The orthogonality relations tell you that if you multiply a matrix by another matrix, you get the identity, say, or the scalar matrix with the order of G on the diagonal. And what we've done here, we simply exchange the two factors, okay? The two matrices. This has a consequence which is purely group theoretical, and the consequence is the following. Well, suppose, okay, let G be a finite group. No big surprises here. And let N be a normal subgroup. And proposition. And we want to compare the centralizer of an element in G and of G over N. So let Gn be the quotient group. So one may think that, for instance, if you take a quotient, then for instance, maybe the group becomes abelian. Okay, for instance, N is G prime, the derived subgroup, and then of course the centralizer is just the whole of group. So perhaps it's become bigs. But there is this fact then for X in G. If you consider the centralizer of X in the group G, and the centralizer of what? Of its image. this is an element of G over n, in G over n, then this is greater than or equal than this. So essentially, going to the quotient groups is the same as going through a surjective homomorphism. And the point is that the centralizer cannot increase when you go from a group to the quotient. I will give a proof of this with doesn't require characters, but a proof with characters is spectacularly short. Of course, we have worked somewhat. And the idea is the following, that the centralizer is this sum, okay, over the irreducible characters, okay? So where here we can put, yes, okay. Yes. So we rewrite this formula in this form. I mean, we are just interested in the diagonal part. So let's write the particular case. So if you take Z equal W, then you have that the order of the centralizer, okay, equals what? Here you have Z, I take it, I mean, if they are equal, of course, they are conjugate. That's trivial. So you have an element times its conjugate. And so this will be nothing else but the absolute value of Z squared, okay? Because you have an element times its conjugate, which is exactly the square of the absolute value, okay? So the order of the centralizer can be obtained by summing over the reducible characters. So here you have characters, and here you have something that apparently has nothing to do with characters, okay? So we first apply this to the group G over n. So the size of the centralizer in G over n of Xn will equal, I mean, it's this formula here, the sum of the irreducible character or the quotient of this value. No, but let's forget about this. So chi is in the reducible character of G over n, and we'll have chi of Xn modulus, absolute value square of modulus, yes. Now that there is an important point that we have done earlier, that if you have an irreducible character of a quotient, there is an irreducible representation. So rho is an irreducible representation of the quotient. Then, of course, you can compose with G and you obtain a representation of G, okay? So if you have a irreducible, in particular, if you have a irreducible representation or character of G over n, then this gives you a irreducible representation of G. We have used this, for instance, to determine the linear characters of certain groups. And remember that when we discussed S4, the character variable S4, I showed that S4 has a quotient isomorphic to S3, so we could simply lift the characters over S3, okay, by composing with the pi, the standard, okay? So, and here we see what we have, that if we have say a reducible representation of G over n, you compose with pi, and then you obtain a reducible representation of G, which simply send x to rho of Xn. So when you are summing here, you can say lift all these irreducible characters to some of the irreducible character of G, okay? So this means that this sum will be less than or equal less than or equal to the same sum in G. So recall that there were 3 characters of S4 coming from the characters of S3, and then there was, another character, or perhaps 2, I don't remember at the moment, coming from which were special to S4, which was not in S3. So there might be more characters. So let's write this psi in the reducible character of G, psi x squared. So, I mean, all these become irreducible representations of G, but there may be others. Okay, so this is less than or equal to. Note that this is a positive number. Okay, so the sum, you're summing positive numbers. So if you have more here, this is of course less than or equal to. And because of the formula of the previous, which I have just used here, this is just the size of the centralizer in G of X. So this shows immediately, well, of course, we have worked a lot with characters, that this centralizer is greater than or equal to this centralizer. And recall the point is that for every irreducible representation, irreducible character of G over N, you get an irreducible representation of G, but you may add more, okay? And next time, since we will need to refresh these formulas, it's good that I leave, yes, because otherwise I have to rush, and this is exactly what I don't want to do. Next time we will see a purely group theoretical proof of this. A purely group theoretic proof of this inequality. Because you can prove it. The purely group theoretical means that I'm not mentioning characters, because I mean, this statement that there are no characters, no representations. So the fact that we are using characters here to prove it is, well, surprising. It's not obvious, but there is a proof that just requires actions and the like, and we'll see that next time, and then we'll see how we can apply these formulas here to solve, again, a purely group theoretical problem. And the purely group theoretical problem, but of course I'll repeat this next time, is when I have two conjugacy classes, I take their product, and this will be a union of conjugacy classes. Which conjugacy classes appear in the product? And the answer to this question will be in the we require characters. There is a formula a bit involved, but we'll see it next time. Let me stop here, because otherwise I'm rushing, and this is exactly what I want to avoid, at least in this last month of lectures. So that's it. Thanks.